The objectives for today's lectures are to bring you to understand the concept of graph models that you have already learned it in the discrete mathematics course, and how to represent them using a package in R like iGraph. This is also applicable if you want to study things like this in Python. Like Python has the network X as package, as a library that you can use to perform graph analysis as well. In the big data setting, there is the graph X library that allow you to perform something similar to this. Well, in addition, if you want to do the graph analytics with database directly without having to use the software, there is I think the Neo4j that allow you to do that, and there are a certain numbers of graph database that mainly aim to represent the data stored as graph and then allow you to perform analysis as graph efficiently. Right. And we will also in this lecture look at the concepts of network analytics, like identifying influencer, identifying the cluster of items that are grouped together. During the lectures, there will be a number of exercises that I would wish that you would do, and I will leave time for you to do those exercises during the lectures if you want, about 5 minutes per each exercise. These exercises would ask you to just import the data, manipulate the data, and then perform certain analytics with the data. Okay. Okay, let's get started. So in order to do the network analysis in R, you need to install these two packages. The first one is at least these two packages. The first one is the package, the library called iGraph, right? The second one is the StatNet. The first one is used for graph representation, that you can create a graph from, say, metrics or from the adjacency list representation, the tabular representation like that. And the second one, you can use this libraries, StatNet, to create to perform analysis of the data that you have. Right. So let's start with representing graph as the data structure in R. But before we do that, let's first look at how can you represent the graph as mathematical construct. Right? Because the important things about using computational language, whether it's R or Python or Java or others, to work on your data is to use mathematics to help you. Because when you represent things as the mathematical construct, then you can implement them in the computational machine. So for the graph, let's think about this as the revisions of the thing that you have already learned it in your discrete mathematics course last semester, I think. No, the first years. Right. So for graph or for network, you have these as the node. These are called nodes or vertices. These nodes or vertices are the representation. Usually, is used to represent the entities that you want to study, like individuals, like places, intersection, and other things. The thing that you want to study, and the edge represent the relationship between the nodes. For example, if you think about the node as customer in telecom company, the edge can be the calling between them. If you think about the nodes here as interactions and places, the point of interest on your map, then the edges can be the direct link, the road between them. If you think about the node as, say, node type A as customer, node type B as book, then you would have relationship between people and book, and then you may be able to infer the whether a group of customers like something similar to another group of customers or not. So by representing your problems as graph, it allows you to perform analysis as in the more than just two relationship, but in terms of larger structure. I would say it is more like a structural inference, that you want to perform inference to the structure of the data that you have. Inference means summary and make claims about things. This is called the undirected graph because there is no direction in the edge part. This is a directed graph, although it might be written differently depending on the software type that you use. This directed graph contains not only the node and the edge like the undirected graph, but it also contains the direction in the edge. That means it tells you the direction of relationship. Or in other words, you can use this graph to represent the direction of relationships. Like you have this account following another account, like in the clubhouse, right? There's a following and follower. Right? A following-follower relationship can be represented as this directed graph. These two graphs, or I would say any graph, can be represented as an adjacency matrix. An adjacency matrix is the matrix that you represent relationship as an element 0 and 1. Right? 0 indicate there's no edge between the entity, and 1 indicate that there's an edge between entity. Okay, let me use this. Let me set up this iPad a bit. I can write that to you. Need to switch the account. Bear with me for a moment, 1 minute. Okay, and I gotta join in this. Right, and by writing it this way, I'm actually denoting the sequence of node as following. Right, so this would mean from node. Yeah, let me set it up like this instead. Right, from node 1, node 2, node 3, and node 4 to node 1, node 2, node 3, and node 4. That means this one is the relationship between element 1 to element 3. So if you were to identify that in the graph, this 1 3 would be this line. Right, the relationship from 1 to 3. It is represented as the 1 in that graph. Why for this say 4 2? Right, 4 2 is the is which line from the graph? You see that, okay, it should be the line from 4 to 2, so that should be this line. Right, now you can see the relationship between the representation of the graph as a matrix and the values, the matrix and the graph structure. How do we create a graph using iGraph? Here is the way, but before that, let's use just metrics to represent the things in the graph and then play with it a bit, right? So I will start with creating just a matrix with the name in the row and column as A, B, and C, like this one. So instead of typing, I'm going to use the file that I have already prepared and then run from that. Is M6-1, M6_1_ network representation. Before that, let me let me set the working directory to this one. And yeah, I have not installed iGraph yet for this computer. Let me install it. The iGraph and the statnet. That one is installed. Packages and statnet. I will have to use it anyway, so yeah, that's it. So here is the first few line of code. The first line of code, I create a matrix. Actually, you can think about it as a vector, two-dimensional vector A, and then I can type it to show you here. This is A, right? To plot A, it looks like this, just 0 1 0 1 0 1 1 1 1 0 1 1 0. So this means the relationship between nodes that we want to represent. And in order to instead of letting them be something like this, which is hard to read in terms of the sequence, I will put the name into the columns and row, so that when we create a graph, it will use the column and row names as the network, or as the node name, right? So here I define the node names as ABC and assign it to the dim names, the names of the dimension. This is to be the list of node name in both dimension and A, right? So now I have this this matrix as relationship between A, B, and C, between the graph, the node A, B, and C, right? And next, that the thing that you have already learned it in the in matrix, that when you, I don't know if you remember it or not, in your discrete mathematics last year, when you multiply the matrix together, you have actually performed the operation. That operation is called traversal. The metric the graph traversals mean moving from one node to another node, right? When you multiply the matrix, you are trying to see what would happen if you traverse the graph 2 times, right? How many ways that you can travel from one node to another node. So before we begin further, let me go back to this one, and now let's draw a graph that represent this that this matrix represent, right? So we have 3 nodes, A, B, and C, right? For A, B, and C, now the relationship is from A to B and from B to A. Well, let me put it this way. And it doesn't matter if it's an arc or a straight line. In this case, it just denotes relationships, nothing else. And lastly, the B to C and C to A, right? B to C and then C to A. So this is the graph that this metric represents. Okay, now let's go forward. When you multiply the matrix, this operation is matrix multiplication. This is different from A multiplied by A, right? How does it differ? The above is the matrix multiplication in the sense of mathematical matrix multiplication. While downward here, multiplication like this denote element-wise multiplication. Right, this is element-wise multiplication. While the above here is, it's matrix multiplication. So you know matrix multiplication, right? Remember, is the using the column vector to calculate the dot product of the row vector in order to get one value at specific index. This is the thing that you have learned since high school. And I would say the work in data science require the understanding and the use of metrics a lot. So you probably need to revise those concepts in linear algebra, in like understanding the vector, the line, and the unit vector that is perpendicular to the line, the vector projection. What else? Eigenvector, eigenvalues, the thing that you have learned that I think in your mathematics 3. Yeah, those are really crucial concepts in the further studies in data analytics, both in, well, I would say in either data analysts, business intelligence, business oriented, or as data scientists that you want to go into the deep mathematical understanding to bring about the models that would be able to represent the phenomenon, or whether you want to study as the technical aspects of data analytics in like data engineering, or AI engineering, because you need to understand how these are implemented in order to implement the workflow, in order to implement the AI operations like in the learning process. Right. So I would suggest that if you want to go to this path, revise the mathematical concept that you have already learned it in Math 1, Math 2, Math 3. I would guarantee that you need to use all of them in this case. And also statistics. So all the math course that we have in this in your program. Okay. Right. So matrix multiplication, what does it tell you? If you take a look here, from the path from you can see that there's value 1 here in A to A. What does that mean? This means that because you multiply the matrix together, this one actually indicate that okay, if you traverse 2 times from A to B and back from B to A, right? You can traverse from A to B and back from B and then back from B to A. Traversing 2 times, you will equivalently moving from A to A. So this is like a loop, right? It's like a loop that A has moving from, you can move from A to A. Although for this graph, you can write it differently like this. Like this, right? This graph is the representation of traversing 2 times in this matrix. Okay, so multiplication results in the movement in the matrix, and the multiplication results in, because it's the movement, it gives you the path length, the path that has length of 2. So you know that there is a path between A and A with the length of 2. There is a path between A and C with the length of 2. Okay. And when you multiply it many times, this is multiplying 2 times, path of length of 2, multiply it 4 times, you get the path in the length of 4. And let's start with this one first. A to B, B, well, I should write. You get A, B, and C. You have an A to B, B to A, B to C, and C to A, right? And for the length of 4, you can see there are number that is not 1, right? B to A, there's 2 here. What does that mean? Let's trace the path from B to A with the length of 4. What are the possible movement or possible paths that can be between B and back to A? First, from B here, let's start going back, because, well, you can go to A for sure. You can come back to B. This is 2, right? This is 3. Oh no, that's not possible, right? That's not part of length of 4. So what can I do? Then I can go down here, going up 1 2 and then go back down here. No, it's actually I start with B, from B to A. Yeah. 1 2 3 4. This is the first part. Another one is let me use another color. Right, another one is 1 2 3 and 4. Right, you have two possible paths to traverse from of the length of 4 to traverse from B to A. That's why you get the result of 2 there. Okay, so in other words, the one if you represent the graph as adjacency matrix, and then when you multiply the graph together, the result that you got is the number of paths that would let it travel from you travel from one node to another node. Okay. Right. That is one way of representation. Another way to represent the graph is to use the thing that is called the adjacency list or the edge list. Right? You can use the edge list as the representation. Using the edge list representation requires you to have a more compact representation, because now you can see that, well, the downside of this representation is that the number of columns would grow equaling to the number of rows. And if you have a sparse matrix or a sparse graph, what is a sparse graph? Just think about it. How many friends that you have in your Facebook, and how many Facebook users are there? Right? In any types of social networking, right? There would be this phenomenon that is actually called the small world phenomenon in the graph graph models. That is, well, you will encounter actually that there are like multiple phenomena there, but I'm not going to that, otherwise it will take too long. But put it simply, that is the number of the number of friends that you have would be differ a lot, but it would be hugely differ from the number of nodes out there. And if you were to represent it as the adjacency matrix, that would mean that there would be a waste of space, because there would be a lot of zero out there instead of one. So representing it that way is not okay. So there's the thing that is called sparse representation in terms of matrix. Sparse representation, like a sparse matrix. That is, instead of representing it as an adjacency matrix like that, you can represent a matrix as the relationship between nodes. Right? And that is the edge list here. In the edge list, you can represent the graph as a list of edge. So for this one, we have edge number 1, edge number 2, edge number 3, and edge number 4. Right? In R, it's just a matrix of two columns. One is the first edge, another the from node and the to node, right? The source and the target node. And in case of undirected graph, this list would not have direction. Right? For the directed graph, you would need to have like the from node, right? The node that it is coming from, and the to node, the target node, that that it has to point to that one. Okay, now let's see how you can create a graph object from different way, starting from creating from literal specification, from specifying which node relating with which node. So here I use the library iGraph and use the function graph from literal. In the graph from literal, you need to input the list of node that connects from one node to another node. Right? The minus indicate that there is no direction in this relationship, while the minus plus indicate that this is the relationship from B to C, okay, and then C to A. And then I got this G, And then you can see down here that there are certain, because I use directed notation, it overrides relationship to represent only the directed graph, and you get the iGraph object here. We will talk about the notation here later on. Okay, so this is where the fourth is like you can create the edge list. Let me run it in case I need to use it later on. Well, you don't need to run the install iGraph because here I have already run it. No, I mean, if you have not installed, you need to install the iGraph, but I have already done that, so I don't need to. So load the iGraph object, iGraph library, and there will be graph from. You can type and then tap and then see what are the possible commands that are available. This is graph from literal, means that you specify it literally. And when you look at the G here, it contains the iGraph, and this is the code denote the iGraph object to tell you that this iGraph object has this kind of serial number. And these are these would be the I would say the indicators that are of the types or the properties of this iGraph object. D indicate that this is directed graph. It has direction. N indicate that it contains name. It contains an attribute names. Okay, and 3 and 2. 3 indicates number of nodes. 2 indicates number of edges. Right, the number of edges. So down here are attributes that contains in the graph. First is this is attributes of here vertex as character. I see here is character. So if you take a look at the manual, then there will be a more thorough explanation that you can dig in, right? And edges from this graph, this is the graph contains this B to C and C to A, right? So graph from literal allow you to create the graph, and it represents these relationships. And there will be a way that you can plot this graph later on that I will show you. Okay, you can create graph from other types of as well. This is the way that you can create graph from an edge list, and you need to just define that. Okay, you need graph from edge list, and then use the matrix to contain the edge list, and indicate that the direction is true. Directed equals true means that this should be the directed graph. And the result here, G will change from the above to A to B, B to A, B to C, C to A, the one that I have already created. And yeah, you can also create a graph from data frame, right? For this one, in order to demonstrate, I just change from edge list to data frame, df, and then I use the create graph from data frame. Then I get the same result with directed equal true as well. Here it is, and you can create it surely from the adjacency matrix here, the adjacency matrix, and it results in the same graph that we have already talked about, right? The A1 that I have redrawn. We will see in the plot later on that it did look like what I have already did draw to you. Okay, this is the using adjacency matrix. Right, please note that here the names of the graph will be different. The names is automatically generated here. So they are differ from one to another. Think about it as just like the pointer reference. Yeah, it's the name of the graph. Right, so these are the routine that you can use to create a graph, and there are plenty more that we will take a look at. Like you can read directly from the files and create a graph. All right, let's move on to the next topics. Okay, So first, I show you how to create and import a graph. I also introduce you to the package iGraph and the representation of graph in R. The next topic is the standard structure of graph. We will see different types of graph that are, well, that you may have already learned it, and you may want to know whether there are a simpler routine that simpler functions that would allow you to create those type of structure. Because sometimes instead of manually specifying or creating it from the program, you can generate those graphs by using the functions that are already in iGraph here. And think about this as the revisions of the graph that you have already learned it in discrete mathematics, like the complete graph, cyclic graph, the wheel graph, what else? Bipartite graph, right? And many others. Start with this one. Right, you can create graph by using make and underscore, and there will be a types of graph that you can create it. This first one is the, well, let me open the file. Second one, standard structure. Right, and this one I also use the function plot, which would allow you to plot things. Right, there is actually this is a generic function in R. Generic function means a function that take in any types of object. Depending on the library that it would override this one. So plot.igraph or plot.graph would generate the graph for you. Right? And you don't have to type plot.graph, you can type the plot and you have graph object, and then we use refer to this graph object. Okay, so the function called make tree would create a tree with the number of nodes equaling 27, and I think, and well, you can look at the library, you can look at help by make tree, right? And here is the number of vertices that you want to plot. And children refer to whether you want to create a binary graph, ternary graph, right? Or what types of graph that you want to create. So by using make tree, right, we now have the graph G looks like this. It would generate a sequence of graph because I specify that the number of children should be 3. That means when I plot the graph here, well, in the plot there will be a number of parameters that you can specify. The one that I used here, because when I teach this one in using projector, it look worse because of the projector scaling. So let me remove it to see if it would help if I plot it on my own computer here. No, not really. Well, you can see that this look terrible. Right, the edge arrow size look terrible. So, well, I want to make this graph look nicer. What I would need would be that I would need to maybe increase the size of the figure. That's one thing that need to be done here. Or increase the vertex size. Well, how can I do that? Increase the vertex size. Let me check plot.igraph. Plot.igraph contains a number of things. Well, there is this mark group, mark shape, mark column, mark border, and others. Parameters from iGraph plotting. Size. Can I use a size? I think not. Yeah. Let me check. Maybe I need to use vertex dot size. iGraph. Let me check in the manual. It's actually vertex dot size, right? Yeah. Maybe I need to increase the scale of this one. Yeah. this is better. It look worse here, but you can see that here you got the relationships between the node and the edge looks actually nice, I think. But you can play around to shape this graph to be more beautiful than what I did here. But at least here you can see that this 1 point to 2, 3, and 4. Okay. Let's look at different types of graph here. This is the tree, right? You understand it that the trees contains the parent and childs in discrete mathematics. You can create it using the make trees. It's for the n-array tree, right? The n-array, like binary tree. Next, the click or the complete graph. You can make a complete graph by using a function called the make full graph. Make full graph, we create complete graph with the number of nodes equaling to the number of vertex equaling the number of the value that is specified here. That means I need to copy all this to all of that. I make full graph, and plotting, you get this hexagonal relationship, right? The makes full graph give you the full graph, like fully connected graph. Then the next one is the lattice. Lattice is like a grid. In order to generate this grid, you need to specify 2 dimensions, the number of column and number of rows, okay, and create a lattice. This is the lattice that circular equal false. You get this one. Well, I removed the labels. Set it to NA to remove it. Because, well, it has to see if you have label here. Now try to play it here. If you set circular to true, what would happen? And you get this circular lattice. That is, instead of having the grid layout, now you have the circular layout that you have it in layer. And then it will connect in layers. If in his as file is generate grid. So this is whether you want a grid in the square manner, or if you want the grid to be in the circular manner. Next one, you notice at the star network connection, right? So think about this one. What types of relationship that the first one first? What types of relationship you want to represent it as tree? Maybe the snowball sampling, the forward mail. Yeah, this is something like that. Complete graph. You can represent the relationship like the friendships between people, the traversal between web using the complete graph with the value equals 0 if there's no such connections. Lattice. If you have relationship that in lattice, that is in the grid, then you can use lattice. For the star, if you have relationship like one connect with other, like the router and the computer, then you can use star representation. Right, and those are the pre-existing structure that you can create. The next one is the way that you can create graph from file, right? You can create a graph from file. This is the graph that you can use is the dolphin edge. It tells you a relationship between dolphin, whether this dolphin would follow which. So that is the relationship between from to, the social network of dolphin. And then you can create a graph from data frame based on this one, right? And then specify this column from and column to, and it will generate the graph for you. So here I imported as dolphin edges. Looks like this one. Imported to graph, and when you plot it, it looks like this. Sorry about this one because I think I need to set the vertex size to say 20. Then zoom in. Yeah, you get this one. This would look better. You need to play a little bit with the vertex, the plot to get the layout of plot, and then you will get graph that looks nicer. But now you have representation of graph of this dolphin in the in your our environment. Let's look at dolphin. Here, you can see that it shows you the edge that it is from CCL to double, DN to feathers, DN12, DN21 to feather. Like so, it has certain relationships between this, and you can note that the node contains some weird space. This is because the string that is in the original data. If you want to clean that, need to clean that before creating this types of graph. Okay, and you can get the vertex list. You can get the you can list the vertex out because here's there is the dolphin vertex, which is the names, and you can use graph from data frame vertex, dolphin edge and dolphin vertex, because in dolphin edges you can see that, well, names look weird, right? So you import the name from elsewhere and then create a graph by using the vertex name instead, because it's already cleaned. When you plot it, you get the graph that looks better. Yeah, well, you can look at this dolphin again and then see that now that it's not fixed. Did I use the same one? Yeah, probably it's because of this dolphin vertices has not been cleaned either. Let me check. Dolphin vertices. Oh no, this dolphin vertices contain not only the name but also the gender, right? By importing it in, it means that each vertex would now have the gender notation. Let me zoom in here. Each vertex here, it would now have the gender attributes. So if we look at dolphin object, right, now instead of having just attribute in names, now we have attribute in gender as well. Okay. After creating the graph, you can export that using the right graph. Okay, now you have the graph ML object, which can be opened with author program. Okay, so then these are the possible format that you can use, and then you can use this format to import to other types of program. Okay, now it's time for exercise. Try it a bit, load the data set, and check if they are what types. Okay, what types of data set are there. Well, I give you, for this one it's easy, so I would give you 3 minutes to work on that. Remember, check whether this is directed or undirected. Okay, so in case that you haven't worked along with me, haven't been working along with me here, import the data set into iGraph, because we'll play with it along later on. Okay. And then try to plot graph and make it more beautiful than mine. Well, give you 3 minutes. Now it's 54, so let's end around 57. All right, if you have questions.
Where is the link for analysis?
Again, please.
Where is the download link for analysis?
In the groups. In the Facebook group, I think I post that, right? Yes, it is in the Facebook groups. Right, I'll be back. Okay, so hopefully you have already imported the data in and install iGraph package. Now let's move on to the third topics. Right, there are 5 of them today. The third topic is to manipulate your network, right? Manipulate your graph. So let's see what are the functions that will allow you to do that and what are the meanings. First, let's take a look at the attributes. In the iGraph, there is like when you install iGraph, it will have the additional package called iGraph data coming in. You can load the data, and there is the US airport, contains the data about connection between the airport. Let's take a look at that. Okay, third one here. Yeah, I have not installed iGraph data. Install it. The iGraph data is the data from the creator of iGraph. It contains a bunch of useful data for demonstrations. So load the library iGraph data, use US data airport here, click it. Now you can see that it is a list. So in itself, it is hard to understand if you just looking it as the data structure. But when you type in US airport, then it will show you that this is actually an iGraph object. It contains, this is an iGraph object, a directed graph containing name and having 755 vertices and around 23,000 word edges, right? And for each vertex and edge, it contains a number of attributes, right? ATTR denote that the vertex and edge may contain some values, right? It can contain the name of the, well, that's the name of the graph as character, the name of the vertex level as character, and city and position. So because and this would indicate that the airports contains this attribute, because now airports are represented as vertex. And the connection between airports are the flight, right? So it has this carrier as an edge and the character type. Departure as numbers probably denote the departure time, the number of seat, the passengers as number, and the aircraft and distance. So these are the attributes of edges. All right, and you can view those as when you use graph attribute, it will show you that this is the graph name, the attribute of the graphs. So you know that these graphs contain the names, and that name is US airport. For the vertex, by looking at vertex name, you can see that there are name, city, and position, and then you can use vertex ATTR to retrieve the attribute of the vertex. Say we want to let's look at the cities. Then it will show you the list of the. Let me scroll up. Like it will show you the list of values for this attribute. Right, so vertex attribute names give you a list of attributes. Vertex attribute allow you to retrieve that attribute to view. So what are these attributes? Right, these are descriptions that are attached to the nodes. Think about it. If you use database, this would denote the like a master table. Right, it would be like a master table that tells you that these values associate with the elements in the table, right? Why the edges? Usually in the edges it would be the transaction table, or the table that tells you associations between entities, right? You can also view the edge attribute using edge attribute names, and then retrieve the values, the list of values from those by using edge ATTR, and give the graph and the attribute, and then it will show you the list of this. Is actually carrier, object carrier not found. What did I do wrong? Oh yeah, I used this carrier here, so no. Yeah, so by retrieving carrier here, you can now see that, okay, these data actually contains I would say duplicates value. Why is that? Because the data itself here represents the airports and the flight, each flight between airport. That means there can be multiple, well, one like British Airways can have multiple flights for sure, right? And it will represent in multiple rows and multiple edges here. Okay, so this is the way that you can retrieve the attributes and by using edge ATTR and vertex ATTR and graph ATTR. If you want to know the names, just the names of these, you can use the function called V and E to retrieve the vertex and edge. Where is it? Yeah, you can use V to retrieve the vertices and E to retrieve the set of edges. this is like a subset. It's like from the full graph you retrieve out only vertex, and then you can perform indexing with that, subsetting it using index and using name to retrieve elements from those, right? So by that means by using just v and then the airport, then you get the list of vertex. Then you can subset the first 5 using this one. This is like a list, and because in that sense, if you use JFK here, now you retrieve the JFK vertex out. And if you use multiple square bracket, it will allow you to access the attribute of this vertex. And then you will see that there are like multiple attributes in this vertex that you can build. You can add additional attributes to the graph, and that can be done manually as this. For this one, I access the attribute cities by using the $ city. In order to add a new attribute, say the groups. For this, there's a sample A and B is like the sample function would generate the random sampling between A and B with the number equal to vertex count. We count is a function, you know, that's vertex count. Replacement equal true, so that means I can sampling to the same element. And so you have like a vectors of A and B equaling a number equaling to number of vertex of this graph, and then assign that to group. Now by doing so, you have an element called group as an addition to the authors, right? So this is the way that you can manually assign vertex, right? For the edges, so this is the way you can manually assign vertex. For the edges, you can retrieve the list of edges by using because you need to have certain notation to retrieve things. For vertex is easy because you can use the vertex name, but for edges that would be difficult because they're usually, when you want to refer to an edge, you probably need to have like a pair vertex to compare to. And in here you need to specify the pair vertices from JFK to Boston, and this operator is an undirected operator telling you that if there is relationship between JFK and Boston, right, this percent hyphen percent, right, then you need to show off this. Then you have all JFK to Boston without regarding to the direction. And in order to it's like JFK to Boston with direction and retrieve only the carrier because there are redundancy, use the function unique to get the list, and then you get this would be like a query to the database to say you want to find the airport, the carrier that can allow you to travel from JFK to Boston. If you think about using deploy R, that requires a number of steps, right? You need to select filters, right? But for graph, it's just one line of code and allow you to retrieve the things based on graph structures. So it is nice in retrieving data from say, okay, I did not put the direction in. Let's put the direction in. Okay, yeah, you get the list of direction here from the graph structure, because think about it as a graph structure allow you to retrieve it very fast, because now if you look at the number of elements in this graph, it's actually quite a lot, like I think 300,000 something, right? So you can instead of say just using one node, you can use a group, a set of vertex to a set of vertex. So this would be like a many-to-many mapping between a set to a set, and in database this would be complicated, right? You need to have like nested queries inside the nested queries, and that would be complicated. For the graph, what you need to do is to create a set and then use that vertex set to be association with another vertex set, And then you can use the same old function, the edge function, to retrieve the like filter it out and then get the edges that has these vertices in connection. First creating the in Cal and in NY. Now you have an airport in California, and in Y you can type it in to see. These are the true and false for the airport. They are in Cal and in NY. The grep out here, it match using the regular expression. It would match the CA $, means that CA has to be at the end of the string, and that list of strings come from the list of cities. So for this one, I would know that which one is in California, which one is in New York, and then using the edge to retrieve index and retrieve it out, and you get the list of flight from these two states. Okay, so these are the way that you can manipulate the graph, extract the part of the graph out. Now is your exercise. What I want you to do is to count the number of male and female dolphins in the pot, in the data, and add weight equal 1 attribute to every edges in the dolphin network, and then verify that you get that out. Okay, I'll give you this for this one about 5 minutes. So there will be no break today because it will be like this. I will show you how it works, and then now it's your turns to work on. It shouldn't be hard here. Actually, just I think 3 or 4 commands allow you to do that. Okay, from the previous slides, now your turns. Right. First, count the number of male and female in the data. How to do that? Filter, vcount. Second, add the weight equal 1 to every edges, and then verify that it works. Right. So you have 5 minutes. So now let's resume it again on 10:15. Okay. Yeah, I'll be back. Now let's see how it works. I shared this right. Okay, let's share that. Okay, what I asked you to do is to from let's say I need to so I asked you to use the dolphin data. And from this dolphin data, what you need to do is to count the number of male and female dolphins in the pot. How would you do that? How can you do that? You need to access the attribute from the dolphin, right? The attribute that you need to access is gender, and that would be the vertex, right? Vertex attribute. And the vertex attribute for dolphin that you want to access is gender. And now you have male and female. Yeah, then you can just use table. Then you have the number of male and female and unknown, and that would be these numbers. So you can see that this is very simple. You can use vcount as well if you are grouping the data based on these and then count them. So this is for the first one. The second one, I asked you to set the weight of the attributes to 1. Add weight equal 1 to every edges in the dolphin network. How can you create such things? Let me put it back some slide. See how can you create attributes. You can see here that you can add attributes using the reference to the object and then $sign the thing that you can assign, but these are for vertices. How about the edges? Well, same ways, right? You need to access the edge first, E, and then dolphin. Then you are now accessing the edge level. Edges level. You want to add attribute, you can just type in weight equal 1. Then now let's take a look at the dolphin data. Oops, dolphin. Yeah. Now it contains the weight that contains E as the attributes of this graph. Sorry, it contains weights as attribute for E, for edges, for this graph. Right. That's for the exercise that I asked you to do. Just a few lines, of course, as I said. Okay. Now let's go further. Now we are going to induce the subgraph, create a subgraph. But in order to create a subgraph, you need to have some reference to create. Say you can create a subgraph from vertex for sure, like putting a set of vertex, and then you are creating subgraphs from the vertex, right, by using induce subgraph, and think about it as the flight that are in this set. Okay, so then we can extract it out. I don't think that's induce subgraph here. Yeah, and then you get all the flights that are, and then these are 381 of them, right, that are within California in Cal. Okay. Right. Though you can see that now we move on to manipulating the graph to get another graph. Right. You get the subgraph. You can create another graph as well using by inferring from one node and then expand from that. Right. We call that neighborhood. Neighborhoods are the nodes that are close to the nodes that you are inspecting. Right. For example, if you have the road network, then the neighborhood would be the places or intersection that you can reach from that particular point. If you think about the friends network, then having neighborhood means you are retrieving the direct link between people. If you have email network, right, the network of connecting between people in organization, retrieving ego graph would mean retrieving the contact list that are available out there. So you can see a number of useful applications here, ranging from just retrieving the set of data to performing a deep analysis. Right? So that is called ego graph. In ego graph, like ego from one person, then look for another. You have like using the object, the iGraph object, and then put in some nodes. Then it will look from these nodes and then create an ego graph according to the orders. Order will give the number of traversal, the number of steps from this node out there. By order of 1, it means just one step ahead, one step outside. Order of 2 means 2 steps from that one step, another 1 step from that 1 step. So 2 steps from the nodes. Okay, let's look at this. For just ego, it gives you a list of what I can show you the 2 vertices. It will give you list of vertices from this node. Right? So ego graph, function ego retrieve the neighbor, retrieve the vertex. Right? Just give you a list of vertex. Why? Just like subsetting one function v, those give you a list of vertex. If you want it as a graph, then you can use make ego graph, right? And then the object, the node that you want to infer to, the orders, and yeah, from that you can plot it, but still a lot here. Take a while to plot. Yeah. It's hard to render because it contains lots of nodes here. You can this is the ego graph from JFK, and there are a lot of places that you can reach from JFK. That's why you see this graph. And this is order of 2, meaning that going to that airport and going to another one, right, like 2 hops, and it will be complicated to view in here. another manipulation, you can that instead of not just about attributes that you can add, but also the vertices and edges. You can manipulate them, right, by adding in the list of vertices. This is vertices is used to create vertices. Edges used to create edges, part of the graph. Then you can add them. This is the empty graph. For this one, I'm adding the vertex A, B, C, and then add edges A to C, B to C, right? And then let's plot and see the result. This is the result, and you can delete it as well by using this and refer. This is like just normal subtraction, but you need things to compare to. So by retrieving the vertex and then say A, you are actually retrieving an object vertex and then subtract it out of G. The result would be now that G would not contain vertex A, and the element related to vertex A like edges would be removed. Okay, and so now you can see that this allow you to flexibly manipulate the graph. And it's quite nice in this way that you can add the vertex, and you can actually add another graph to the graph and get another graph as a result. So merging the graph would be easy, right? Overlaying them would be easy by using the attribute manipulations. And extracting part out, think about it as object, and you can subtract and add to another. Will help you in using this network manipulation routines. Right? There are actually others functions that I cannot cover. I don't have enough time to do that here. I would again suggest you to look at iGraph manuals. That would be authors useful function that dealing with the attributes, dealing with the extraction of the part of the graph out. What I can show you here, it should be just the thing that should inspire you, or should show you the way that this is the way that the graph network work, and it helps in calculation, accelerate the way that you can accessing data, and flexibly allow you to merging the data from multiple sources that have relationships, and then inferring from that relationship. That we will look on next to the topic about visualization and analysis. But before that, you get another 5 minutes, but this is a little bit harder than the previous exercise. First, you need to find the edges in the US airport network that have distance more than or equal to 1,500. How to do that? Try it out. And then you need to use the edge indexes to create a long haul flight network. So use edges from the above to create the long haul flight. Okay, think about how can you find edges that has distance more than, you need to retrieve distance, and then you need to compare to 1,500. Then you get the Boolean vector, and then you can subset the edge out. That would be the first question. The second one, because you need to create the edge list of the long haul, you can just use the Boolean vector you retrieve above to just subset the edges. And then the last one is to ask you to create to count the number of airports that you can reach in a single stop from Oakland. Okay, you got 5 minutes. Work on them. I'll be back. Okay, actually I forgot to set the stopwatch, so I really don't know whether this is 5 minutes or 6 or 4 or 3. But in any cases, let's see the solutions. Right. So first we need to identify the set of US airport. The edges in the US airport network that have distance more than 1,500. How do we do that? Let me create a separate section. Exercise. When you use it in this format, RStudio will create a section for you. You can jump between sections in this case. It's easier to navigate to the code. So how can we retrieve the edges? US airport, right? We need to retrieve the edges. Attributes, edges, a list of edges that has one the distance more than 1500. Now if you use edges, you would probably not getting that. You get just edges, and there are 23,000. How do we do that then? Sure, we need to get the edges attribute and US airport. Suppose you did it the same way as I did here, right? And then retrieve the distance. Now you get the distance, and since this is the distance, this distance is in form of vector, you can directly compare it to a while loop. Then you get the Boolean vector, right, to say that is long haul. Afterward, you can use this vector for retrieving the list of edges. It's long haul. Now here you got list of edges, right? Long haul edges. Done. The first question. The second question is to retrieve. I already did the. Did I? Edges. Use edges indexes to create long haul flight network. A long haul flight network require you to retrieve the part of the network that coming from this. So if we look back way that you create, how do we do that? Probably need to we need to have like the flight network where we can create a graph. Then you can just add the edges to complete graph. You can create like empty graph and then add edges, list of edges that you have to the graph. And you have long haul network. That's one way, right? Or you can just use make empty graph, and add the long haul edges. Add a node type to the iGraph n equals 0. Not long haul edges. It's a node type. Oh, not the edges type. Thought it is the edges type. It's unknown types. Convert it to edges. Yeah, convert to edge, and then add it to make empty graph. Need the vertex ID, then you just need to add the vertex ID first, and by retrieving the vertex ID from these edges. Or let's see, there are any other way to retrieve the subgraph from edges. There is the subgraph dot edges as well that you can do to extract it out. So let's try that. Subgraph dot edges, and then you need to use the US airport and the long haul edges. Yeah, now you have the long haul network as a subgraph out. Right, and the last one is to, oh, it's just an equal graph, right? Simple. Last one is to get the how many airports that you can get from Auckland. So a simple way is to just use an equal function and then US airport. And then you need to get it from Auckland. So OAK. And the degree, right? The order equal 1. Now you get 7. Oh, but this is probably not these are probably not not unique. I think, is it unique? Yeah, it is unique. So there are 47 vertices, right? 47 airport that you can reach from Auckland. Okay, so these are the way that you can access and manipulate the data using the graph. Next is how to create a visualization, how to create a plot. And we did that, but there are ways that you can manipulate the plot, and let's look at some of them here using the graph. First, let's plot it using the default plot. When you plot it using plotting function like this, so make ring would generate the ring graph, and I assign the letter 1 to 10. I would assign the letters A to certain values to 10 here, and then add the edges 95, 71, 15, and plot it. And I will get this one as the default plot. Right now, we from this plot we can instruct R to plot it out for us in different way, right? The way that we can do, I don't know if you see this when oh no, sorry, I don't know that you don't see this. Yeah, I did show this a number of times. It look nicer than the one that on the right hand side. You can view this by clicking zoom here, zoom. Then it will zoom the graph, and it actually looks nicer than down here. They don't know that. I didn't know that you haven't seen this. Okay, so you can instruct R. You can instruct iGraph to plot the graph in different way, and that is called layout. Right? You can instruct that use this layout, and it will plot according to that layout. There will be calculations of the location of the nodes that will be performed. For example, this one, LO is the layout in circle. So from G, LO would be the value of coordinate in X and Y that you need to plot it. You need to locate this node onto this location in the plot so that you get the circle layout. And you can add this into plot by adding the layout equals the layout object. And doing so, doing this, now we have the plot in the layout, in the circle layout. So the node will be layout in outside the circle, and then the edges would be all in between. And it looks nicer, especially for the data that is in circle. The next one is the tree layout, right? The tree layout, the grid layout. That you can force it to be a tree well, if your data is a tree, then you want it to plot as a tree. Forcing it as a tree layout, you get the tree. Do you see this? No. Yeah, I need to share it as well. Sorry. Here, right? The tree layout. And next one is the grid layout. Let's see if I need to share it twice. No. Okay, this is the grid layout. It will lay out it as a grid starting from down to up. If you want to know how to reverse and whatever, my suggestion is to read the manual, right? Using help, read the manual, there will be plenty customizable attributes that I would not imagine to cover them in the class. They are too much, too many of them to cover here. Okay, you can use the preset layout. This is the layout that they are called the forced layouts. They are called forced layout because they use the edge weight to calculate the layout, the location of the node. Okay, layout like the layout with KK. If you use the algorithm Kamada Kawai layout algorithm, which each edge corresponds to the length of the spring to calculate the location it should be. The FR, which each way corresponds to the strength of the spring, not the length but the strength, and DRL, distributed recursive layout. You can look at the algorithm by itself here when you're looking at the help. Basically, it will generate the different layout based on the value of weight. Let's see how this would look. This is the FR. Right, so because right now we don't really have the weight is actually all ones, we don't really have the way to use, so it doesn't really give you much of a distribution here. You can look at the help here, layout with FR. Right. Here you can see that you need to specify the weight. I did not specify it. It's force directed layout. In order to specify it, you need to set this vector as to give edge weight. Right, weight edge attribute is used by default. So we have the parameters called weight, and it will be used here. So if this value differs, then it will show different layout here. Like if it represents distance, then it will be used to place the location according to the distance. Okay, and there are many more layouts, as you can see when you type in layout. There are layout, remember bipartite layout, circle, and other layout, LGL, MDS, norm, random. You can play with them to see what will look like. And don't forget to read the manual. Now let's move on to the next one because we want to plot the graph differently, right? So the layout concerning with the location of the vertex. For the vertex itself, you can configure the shape. Instead of circle, you want it to be something else. Like you can specify that you need the shape to be circle and square. Then it will be circle and square according to the shape parameters here. Here, circle and square. Yeah, you got the circle and the square according to the shape parameters. You can also configure the not just circle and square, you can also configure the color that it should plot. So here I specify that if it's vowels, is A, E, I, O, U, then it should be in one color. If not, it should be another color. I'm plotting them. Now you get this. Now you get the vowels in blue and the non-vowel in red. Okay, and you can override the properties of the graph in different way by specifying the parameters directly into the graph object. Like this one, I specify so this should be the circle, size 15, color orange, specified as default. and then specify that this is wow to check that this is a wow, and then if it's wow, then change shapes to square royal blue and the size is larger. And when you plot it, the attribute will be used in plotting. And you can see that you do not need to specify it during plotting, but you can specify it before in the attributes respect to the attribute that are associated with those visuals, and then you get this out. Okay. You can do it the same way for the edges as well. Don't know if these are for the vertex. You can do it for the edges as well by specifying the size, the width. Say the width equal 1. If it's wow, then width should equal 4. Right? If it's VG is wow to VG is wow, set it to 4, and then plot them out. And you can see that there will be an emphasis. There will be an emphasis on the edges of the relationship between wows. Okay. You can also tell the iGraph to plot an edge as curve by specifying the curve, the curvature. That if it's curved, then if it's right, and with this you get the curve for each of these if they are like replicated with one another. Right. For this one, it will create a curve if you have like multiple edges, if they are mutual. Right. If they are, which mutual means if they are mutual, then you get the curve of the degree of 0.3 going on off the axis a bit. Right, and it will generate this graph for you. Right. Last one, I did not have the code here, and because it doesn't seem to work lately. I don't know why. You can group them in the plot by using the group and the group color, and then it will generate the color to cover all of the groups that you want. But I tested, but it doesn't seem to work for me. But maybe I made a mistake there. So maybe you can try it out here. Right. Let's move on to the last section. Right. The last section is on analyzing the graph. Analyzing the graph can be done by first understanding the phenomenon in the graph. There are certain phenomena that I have mentioning earlier. These are like the nature of the graph, the nature of the world, as you see. When you represent data as graph, as a large network of graph, like in Facebook, in university, in email, there will be these phenomena that happens, and it can be reflected in the data, in the graph data. The first one is called the small world phenomenon. The small world phenomenon in the small neural network. Network, the path length of the network would grow very slowly. What does that mean? It means that suppose that you first have a vertex here. Your vertex, like this person, would connect to another person, but this person, another person will connect to another person, but it would not connect in this way, right? It would not connect in this way that you just adding one person, it wouldn't be like that, right? But it would be like this instead. This phenomenon is called small world network because your network would be connected to one another, and you would not have like a long path length like this one. Let's say if you were to connect, there is this experiment that if you were to connect your friends to famous people like Elon Musk, you would need to have like only 6 link, then you can connect to that person, just 6 link, right? So that is the observations in this small world phenomenon. Next is the network usually has hubs. Hubs are vertices that contain a large number of connections. Like, just think about it. What is hubs? For cities, it would be cities with a lot of connection of the road. For flight, it would be the cities, the airport that has lots of flight coming in. Sometimes it's intentional, sometimes it's not. In our body, in the if you look at look at our bodies, some parts of our body acts like hub, like the heart. There will be the hub containing all of the control of neural activities like motor cortex in the brain. Right? There are hubs like that in biology as well. So, and in actually, when I did research in bioinformatics, there are also hub like that in the study of gene and disease. And you would know that these are interesting genes because they are related to a lot of disease. That means it might relate to certain regulation in the biological function of an organism that relate to that thing. So analyzing network would reveal these types of associations, and you will be able to further look into the relationship. Sometimes you can uncover the thing that has not been discovered, like the gene that no one have known before that they are associated with the disease, and studying that gene might reveal hidden functions or hidden mechanisms that had not been known before. So that is actually the holy grail in text mining using the network data. Clustering, when you have knowledge network, the feature that you might want to look at is the groups of maybe group of friends, group of connected components, so that when you know those groups, you can perform different action like give them advertisement, looking at association to understand it more, like that. Okay, now let's take a look at the functions that will allow you to accessing those attributes. The first one, in order to analyze the structure of the network, you can describe the networks by its connectivity, right? Its degree of connections to other vertices. What are the degrees? In Facebook, degrees are number of friends. In Twitter's, degrees are maybe how many retweets you got, right? Maybe your reputation. In co-author network, in literatures, degree are the number of work that reference your work. So it might tell you how reputable you are, right? In the road network, degree would indicate how many roads that connect to these intersections. So looking at degree would give you how busy these networks are in terms of relationships that you want to represent. So dolphin, right? We want to know dolphin, on which dolphin follow which dolphin. And associations, usually in environment, there will be like the one that follow another one. So to extract that degree, you can use the function called degrees, and it will retrieve the degree of each of the element out. You can use head as well with the let's say degree dolphin. It contains like a list of value of the degree value, and plotting histogram will give you the histogram of the degree, so you know that okay, there are a lot of them that have only 1 or 2 degrees, knowing it's just 1 or 2 dolphin friends, but there are just a few that know a lot. So this would suggest that the dolphin network has certain hubs. Some hubs will connect to many others, right? And if there is a new dolphin coming in, it would just add to maybe to the hub, to the main core of the network. So the path length and the total path length would not increase a lot, the width of the network, right? Think about moving from one dolphin to another dolphin. The longest one would be the width of the network. Having the new one coming in usually would connect to the core one, not the like the island one, and that would not increase the width of the network much, the length of the path in the network much. Okay. This is the degree. Clustering, right? You can extract triangle triangle relationships. These triangle relationship is refers to as clusters in the graph clustering, or sometimes called a motif. This represents the transitivity of the network, that if A know B and A know C, B should know C. So they are like a tight cluster in the network. By analyzing the clustering index of the network, it allows you to assess the connectivity or transitivity of the network, right? The global index would indicate how tight the network is. The local clustering index would indicate which node is connected to a lot of other nodes. It would tell you the importance of this node in the in the network scale. Okay, and that can be done by using transitivity. So I created this graph out, and using transitivity global, we give you that this is 0.6 connection, and the node 2, node B, is the most important. The last one is not, because it cannot form connectivity with another. This is the node E, has only that doesn't have any motif. Doesn't have any triangle that is possible to count. Okay, this is the transitivity. The path, in graph theory, path is a sequence of vertices or a sequence of edge starting from one vertex and ending with another vertex. You can get the path like using Dijkstra to find the shortest path, using shortest path, and then from and to. It would give the shortest path from one element, one entity, to another entity. I'm not going to cover the extra here. You have already learned that in your discrete mathematics class. Here is the measurement of diameters. Diameter is the measurement of the shortest path. I would say that, well, yeah, the shortest path between every element, and then you get the maximum value out, and that is the diameters of the graph, say the width of the graph. Right, so you can extract the shortest path out using the function shortest path, and then get the shortest path here, sp.si v path. If there are multiple shortest path with the same length, it would list as multiple elements in the list. Diameters can measure the width of the graph. Right, now is your turn. You got 5 minutes to first find the vertex with the highest degree, the most famous, the most popular dolphin in the network. Right. The second, find the vertex with the highest local clustering coefficient. Again, the one that is the key connecting to another dolphin. See if they are the same. The last one, plot a histogram of shortest path length between all vertices. Look at the manual. You see how to get all the shortest path and the length out. Okay. Well, you got 5 minutes. Yeah, I'm measuring time now. So I got it until 11:06. Okay, I'll be back. Right, let's see how to do that. You need to find the vertex with the highest degree of k, or in other words, you need to find a dolphin that has the highest number of friends. Well, that is actually easy, because you have already seen how can we extract right, how can we extract this degree out. That means what you need to do is to extract, you get this degree dolphin already, and you can just find the max one, sort them. you can see here green has highest degree. And secondly, it asks you to find the vertex with highest local clustering coefficient. And to do that, you need to use transitivity. Transitivity of the dolphin to get the this is global. The type here to be local transitivity, and then get the max one out. How to get the max value of this graph? How do we get the max value out of this one? Well, say you want to see if it's equal max. There can be other method as well. There's an NaN here as well, which is not okay. So, well, need to get the max one out, and actually you can get the NARM. That would do the trick. Max NARM true. Get the max one out, and what should we do? Get transitivity, and doesn't contain the names. And then we need to compare the transitivity to this value, right? And then we get the top one, the two of them here as true, and subset it from the data, right? And what I need to do is to get the list of nodes to subset from the data. So V and dolphin, and subset it out. It's not subsettable. Did I do something wrong here? V dolphin. Oh, sorry. See, a bit confusing. It probably contains this. It's probably contain this now. So what should we do? Maybe need to fill the now with false first. This can be done as well. So I'm extracting it out as because we already have this degree dolphin as the list of name that extracted out. So actually, if you take a look at this one, just let's see here, it's actually index number 21, 22, 23, 24, 25, 26, and 27. Right, 26 and 27 from V of dolphin. It's these two, the same here. So these two are like the those that have the most triangle, but you can see that they are not the same as the one that having highest number of connections. Plot the histogram of the shortest path between all vertices. How to get the shortest path of all vertices, right? And now, if we look at the function, there's the function called all shortest paths, right? All shortest paths of the graph. This graph is degree of dolphin, but it needs from and to, right? So you need the path from all node to all node, okay? And then you can plot the histogram out of that. That means you need the list of node from and to, Right, from here you need vertex of dolphin, and then you get the shortest path from all of that, and these are the result and the shortest path length, and then you can plot histogram of that, all the things that down here. Then you get the shortest path of all of that. You can see that most of them are one, just one step from, because travel from one to oneself require one, zero requires zero, but this is from one to the rest. Then you get all of this out, and the count look like this, right? Let's move on to the last part, is the measurement of importance of the nodes. First one is the degree, the centrality measurement. Centrality measure the center of the nodes. So you have already seen the degree. That one is called the degree centrality, measuring the center of the graph by looking at the degree, looking at the hub. But there are also other measurements of the centralities. This one is called the betweenness centrality. Betweenness measure the distance between vertices by the number of paths passing through that node. So by counting the number of paths that passing through that node, you will know how important that node is. You can see from this one that there's for A, it doesn't require to have path passing through that. Say if you want to go from B to I, you doesn't have to pass A. From C to G, you doesn't have to pass A, right? That's why for A, B, C, G, H, I, these are the nodes that are not in between. That means like this is not an intersection that it has to pass through. So betweenness would say that these are the nodes that between authors. You need to pass through them as the requirements. So for this, you can see that D, E, and F, these are the nodes that are between authors, and E is the highest. So betweenness would estimate this, and the estimation of betweenness is actually quite complicated because you need to find the shortest path between all of the nodes, and then count the number of time that it passed through a certain nodes. So this is the full graph. Let's plot it out. Looks like this one. Assessing betweenness, you got that 16 is the highest betweenness. So you can think about it like the center of this graph is G, right? If you think about it this way, but it's obvious from the graph that G doesn't have highest degree. Rather, D and F has higher degree, right? So if you use degree as centrality measurements, then you will end up with E and F. But if you use betweenness, you will have E as the center, because if you just disconnect it, then the two graphs would fall apart. The graph would fall into two parts. Right, the next one is called an eigenvector centrality. Eigenvector centrality is used to assess what happens if you traverse the graph infinite time, which node that you are likely to end up with. Right, it would tell you the center of that by calculating the eigenvector of the graph. Okay, for this one you can see that D and F has an eigenvector because it kind of connect to lots of nodes. E has lower degree of eigencentrality. Sometimes eigencentrality is thought of as it's the measurement that the node is the decomposition of the adjacency matrix to the eigenvector. So for this one, it tells you that which has a lot of connection, not just a lot of connection alone, but and that are connected to someone with lots of connection as well. That's why in this case we get the D and F that are important because it connect to E connect to F also have a lot of connections like that. And this is in association with this one. This one is called the page rank association. This is in referring to the Lally-Page algorithm and Sergey Brin algorithms that is the core of Google. It used the page rank use the concept of eigenvector that we saw earlier. But instead of just using eigenvector alone, it create a thing that's called transitional matrix from the structure. From the transitional matrix, then it calculate the eigenvector of the transitional matrix. So is more like a model that relies on the representing the graph that we see, this graph. Representing this graph as the probability. Yeah, as a probability. So it represents it as a probability of traversing from, say this is A can transfer to B, C, and D. So you have it as 1 over 3, 1 over 3, 1 over 3, and the rest are 0. And then representing it as the transitional probability, and then it calculates the eigenvector. In the end, what it measures would be the reputation of the nodes. Which node is more reputable, has high chance to be transited to. In terms of the web, it would tell you which node, when you travel it in randomly infinite time, then you end up with that node. Right? So evaluating this, you can see that here the highest degree would be E and F rather than D and F, because D and F contains lots of connection comparing to E, which has only, although is in between the authors, but the importance of its importance in the graph is not comparable to D and F. This is the page rank centrality. So it can tell you that these are the center of the graph. The D and F are the center of the graph. Between this tell you that E is also the center of the graph, because if you remove it, then you don't have the graph. You don't have this graph. They will be disconnected. Right? And these are all the introductions to iGraph. There are also extension concept from the thing that I have covered here, modification of the graph in visualization. In the 5 aspects that I show you, there are more functions that need to be explored further, right? And there's no lab today. Congratulations. That's because one thing is like this just past midterm, and I'm still grading your midterm exam, and I will let you know once I finish it. That. All right. So before we close the sessions, if you have questions, you can post in the groups for sure. If you have questions right now, you can ask me now. Otherwise, let's see each other again next week. Okay. Right. Since there's no question, let's call it a day. See you again next week. On the next week, we will start with the topics that is more exciting than before the midterms and this one. Before the midterm, we look at data models as especially the part about visualization, data visualization. We are creating model of data, the table, to plot the graph, right? To analyze them, to see, to understand. After the midterms now, we will look at algorithms that allow you to predict, allow you to simulate from the data model that you created, starting from the concept of simulation. And we will go through machine learning and the techniques that you can do with R. Okay, there's one question here. Do we have an assignment in data camp for final? Yes. Yeah, I'm preparing that. There will be assignments for sure about learning something. It would not be as much. Oh, don't cry. It would not be as much as many as the midterms. I know that after the midterms there are a lot more work that you have to do. So it would be not, don't cry. It would be less than a lot less than the midterm. For sure. Right? Maybe just a few. Okay, so you kind of force you to look at other materials beside what have been here in the lectures. Okay, thank you for asking. Actually, I plan to announce anyway. Right. Okay, see you next time. All right. For today's, bye. Thank you, everyone.